Okay, I'm John Romein. I'm from ASTRON, the Netherlands Institute for Radio Astronomy. And what we do is we design, and we build and operate world-class radio telescopes. So that is what I'm going to start to talk about, a bit of an introduction to radio astronomy and radio telescopes. And I will talk about GPUs and the high data rates that we need to achieve, how we do this. And at the end, I will evaluate performance and energy efficiency. So, why do we build radio telescopes in the first place? If one wants to understand the fundamental physics of law, you just have to look up into the sky, because this is a great laboratory. For example, it is impossible to create a black hole here on Earth and study its behavior. And even if we could, I don't think it would be a good idea. So we built these radio telescopes to look up in the sky. And there's a lot of things that we do not understand when observing. In the interest of time, I'm not going through the whole list, but if you want to talk about this, come see me after this talk later. So why in the radio spectrum? That the primary reason is that neutral hydrogen, which is the most abundant particle in the universe, is visible at radio wavelengths, and also because the atmosphere it disturbs signals, but at least they go through the atmosphere, unlike many other wavelengths. So we need to build bigger and bigger radio telescopes that create more and more data, because eventually the higher the data rates, the better the instrument and the more science we can do with them. So this is just one thing about this picture. It's not always a dish-based telescope. This is part of LOFAR, which is antenna-based, and we combine the signals of, I think, something like 100,000 of these simple antennas. These antennas are located throughout Europe, and combined they form the biggest low-frequency radio telescope in the world. And this is an overview, a simplified overview of how this works. On the left, we see these antennas. These are grouped, and the data are locally combined. Then we send the data that comes from the field over a wide area network link into a central location, which we call a correlator. And there we combine the data from these different stations in the field. So here the data rates are still high, and we need to do the processing in real time. Only after correlation, the data rates have been reduced so much that we can store them on disk. Then after the observation, we try to detect bad data, throw it away, bad data due to interference, for example, to calibrate the data for ionospheric, basically all kinds of effects, create sky images from them, or create pulsar profiles if you want to observe a pulsar. But on the left, the data rates are high, and the algorithms are simple signal processing algorithms, and on the right, the data rates are much lower, but the algorithms are much more complex. So basically, every radio telescope uses FPGAs on the left. Not every radio telescope, but many use GPUs to combine the data. And yes, on the right, it's CPUs and GPU mixture. But in this talk, I will focus on this part where the data rates are still high. So if we zoom in a little bit, see again, data flows from the left to the right. It's first analog to digital conversion, then an FPGA that does some filtering. That's not packet filtering, but signal processing filtering, creating higher spectral resolution. And then the data, the sample data, is packetized in most often in Ethernet packets or UDP, IP Ethernet packets. Then it goes to a central switch that goes over wide area network links. And then on the right, there are these GPU systems that correlate the data, that combine the data. And the switch does need to do some packet switching because the data can go from any place left to any place right. So this is a simplified overview of what happens in a GPU correlator system. On the left you see the packets arrive, and they first have to be buffered in a circular buffer, basically for many reasons, but an important reason is that the telescopes can be quite far apart. There can be a telescope that is 1,000 kilometers away from the correlator, and there can be one that is close by. And we need to overcome the differences in travel times. So we need to buffer, typically half a second to a couple of seconds. Then we process the data in blocks, and block of data is then transferred to the GPU that does some other filtering and correlations. At least these are the most important tasks. So in the circular buffer, it's just overwritten continuously, and this is a real-time process, so the data must be consumed from the circular buffer before it's overwritten again. So if we look at the past decade, we've seen an enormous improvement in computational performance. Then 10 years ago, the best GPUs could do 2.4 teraflops per second on correlation computations, and now we get 2 orders of magnitude better. That's even 2 years ago that we got 2 orders of magnitude better, and that's basically due to the introduction of tensor cores, which we can find in the GPUs from the last 5 years or so. These tensor cores, that special purpose hardware to accelerate training and inference in deep learning, but we use them for signal processing, and that gives us an enormous performance boost. But if we looked at the I/O, that in the same time we went from 40 to 200 gigabit Ethernet. So what was once a compute-bound problem is now an I/O-bound problem. But last year, NVIDIA introduced this great new GPU architecture. It's called Grace Hopper. And it's not just interesting because it's the fastest GPU on Earth. The most interesting part is with this blue circle, it's the interconnect between the CPU and the GPU. That used to be PCI Express in previous generations, but now it's NVLink, which in practice gives us 16 times more bandwidth between the CPU and the GPU than with previous generation GPUs, sorry. So on the left, you see that there's 4 PCI Express slots. Well, there's not a Grace Hopper system that exposes all of them, but there are systems that expose 3 PCI Express slots, and we can stick in 3 400 gig Ethernet interfaces. Or, well, we did a mixture of 400 gig and dual port 200 gig for availability reasons. But in practice, that doesn't matter. In total, it gives us 1200 gigabit per second of input bandwidth that we can stream into a GPU, at least in theory. But the question is how to do this in practice, because this is really a lot of data. So, well, first of all, of course, get rid of the operating system. That works fine for 40 gig Ethernet, but not for 200 or 400. Start using DPDK. As I will show in the next few slides, copying is a bad idea, and we used the recently added, a few years ago, added support for GPUs in the DPDK toolkit. So what does not work is the traditional approach where we copy the data from, on the left, there's these network interfaces, which we treated as 6 times 200. There's the general DPDK pktmbuf. We receive data into that, then copy the data. That's the first copy into the flat ring buffer, and then a second copy from the CPU to the GPU. That will give us 300 gigabits per second on these Grace Hopper systems. And the reason for that is that we consume way too much memory bandwidth. In practice, there's 340 gigabit bytes per second of bandwidth available, CPU memory bandwidth, but we already start losing real-time performance at approximately 200 gigabytes per second. And the reason for that is this NVLink bus, which, well, it does not claim all the CPU memory bandwidth, but it claims so much that there's insufficient memory of bandwidth left for the Ethernet packets to arrive in CPU memory. But let's not talk too much about approach that doesn't work. Well, this approach also doesn't work, where we place this ring buffer in GPU memory and copy the data directly from the DPDK packet buffers into GPU memory. It will double performance, but again, after 200 gigabytes per second of memory bandwidth use, we start losing real-time performance, start dropping packets. So the only thing that works is a true zero-copy approach. For that, we use the feature that we can split packets, have the packet headers received in CPU memory, and they are also processed by the CPU, and the packet payloads, which is the bulk of the data of the packet, it's 8K, with antenna samples that goes through to the GPU. So the CPU processes these packets. It's not just only the UDP header, but it's also some timestamp information from the antennas, the antenna number, etc. The disadvantage of this approach is that, well, we have 2 times the allocation and deallocation overhead, both for the header part and the payload part. And another thing is that because we had this large ring buffer, the ring buffer is now implemented as the mbuf, the mempool. So we buffer almost 9.5 million packets in this ring buffer. And what we basically do is that, well, for every packet that we receive, we return 1 to the mempool, so that the cache is, somewhat half full. So for the zero copy approach, the GPU has to do a little bit different. It needs to do the DPDK packet processing. But the channel filter and the correlator is still there. It's 2 different tasks, but the packet processing and the channel filter, it is the same GPU kernel. And if we look at the performance, well, recall that this is a real-time application. So if we cut the data stream into 2 pieces of data of 130 milliseconds, we do have 130 milliseconds to process the data. And fortunately, the GPU is fast enough. As you can see, it takes 100 milliseconds, 771 of which is for the filtering and the correlations, and the rest of which is the overhead from DPDK packet processing. And the overhead is caused by the fact that we cannot control where the packets are received in GPU memory. It is received in GPU memory, but at random locations. So we have to look up, every time we want to read a sample, we have to go through another pointer in direction to look up that sample, to find the right place where that sample is stored. And that causes the overhead. But we also see from this picture that there's still 30 milliseconds of time left. So we compute too fast. And that consumes energy. So what we can do is reduce the GPU clock speed to reduce the energy consumption, because high clock speeds mean much higher energy use. And we could go all the way from 1.98 to 1.50 gigahertz. And yeah, that was just about when we started to lose real-time performance. But if you look at the right, there you see the energy use that drops by almost 100 watts. And it's just free. We do the same computations with 100 watts less of power use. And the same trick, we can apply that to the CPU. Basically, we do need 6 cores. 6 cores are barely fast enough for doing the packet receipt and header handling. But we can also do this with 12 cores. And 12 cores does use a bit more power. But with 12 cores, when we use 12 cores, we can reduce the clock frequency, and then again, we almost halve the power use. We can, we can go up to down to 1.8 gigahertz, and after that, we will lose real-time performance. Can also try this with 18 cores, but that doesn't help. So, looking back, We successfully streamed 1.2 terabits per second into a GPU. This is, as far as we know, we are the first to demonstrate this. And the enabling factors is, a mixture of hardware and software innovations. Of course, the bandwidth uplift within Grace Hopper, the ability to split packets in DPDK, and receive the headers on CPU, and the payloads in GPU, use DMA for that. Truly using zero copy, even though that implies that we have very, very large mempools, and an effective use of the mbuf cache is very important. And we saw that, there is overhead from DPDK, but it's manageable. We can deal with it. And this is from our funding agencies. Big thanks. So if there's time for questions, I'm happy to handle them.
Yeah. What do you mean by DPDK overhead?
By DPDK?
Overhead.
Oh, the overhead. The overhead comes on the CPU side from allocating, deallocating the packets from these very large memory pools. And this overhead is much larger than when the memory pool would be small. And on the GPU, the overhead comes from, oh, sorry, that's one too far. That we have an extra pointer in direction because the GPU, if it needs a new sample, it needs to find a place where it can find the sample. And that is through an extra pointer indirection.
Hello. So thanks for the talk. Very interesting topic. And I was wondering, what is the size of the UDP payloads you're dealing with? What's the packet rate? I mean,
8K.
8K. Okay.
Yeah.
Right. Thanks.
For 2K of complex samples in it.
Okay.
Dual polarized. Okay, 8K.